Okay, for this next bit, we're going to use the second derivative approach to find some information about this curve that we're sketching. We kind of know that that's a maximum point when we use first derivative and that's a minimum. We're just going to forget all that because we don't necessarily need that approach if we're just using the second derivative. And this example asks us to use this right the way through with all our points. So the second derivative is a variation of, well, basically, we're just deriving that one again. So f dash dash of x, we are eyeballing or taking a look at the first derivative equation, and we are differentiating it or deriving the next one from this. So we take the 2 that's there, and we multiply it by the 3 out in front. So that becomes 6x, and the power squared drops down one value. So that becomes 1. So we won't write 1, we just leave it at that. The next term that we're deriving is the 12x. The x was a 1 that becomes, well, we can multiply the 1 out to the front as 12, and nothing changes there, so it's plus 12. The actual x part of it falls off. That was x to the 1. X to the 0 is what it would become, and that x to the 0 is just 1. That's all it means, so that's why that one drops off, and the constant has fallen way off again. So when we do a second derivative, or when we derive something like that, so the first original equation had a cube term, an x squared term, and an x term. Notice there were no constants like that. So the x1 term became a constant, but when we derive again, the constant falls off. Okay, so if we had a constant here, this would have looked a little different. But this is the first time we're dealing with a constant in an equation, and when we derive it at all, that falls off. So again, it's dropped a power. It's fallen away to an altogether 0 term. So now we have a shortened equation, but that is the second derivative, so we use 2 dashes, and you need to be able to do that. So the next thing we do now, our step 2, is that we set this thing to equal, we set the second derivative to equal 0, so that we can find points of inflection. Now they are sort of like turning points, but they don't turn completely. They kind of flex. So they kind of start to turn and then turn back. So remember there was types of them, and I've put a table chart in your notes of those. They can do it this way, where this is a stationary point of inflection, because there's a point here where there's a horizontal gradient. Another variation of it is where it's tighter and it doesn't quite have any gradient at that point where it's horizontal, where it equals 0. It just starts to turn and then flicks back around. The other variation of it is in the concavity approach, where you're coming out, say, of a minimum point and up to a maximum point, and where the gradient changes or inflects is somewhere in there. So you're coming around from concave positive to concave negative, and in there there'll be a point of inflection, so I'll just highlight that. So we're hunting for these points now. They're not strictly turning points, but they are points of inflection, which tells us something about what's flicking around and changing in our polynomial graphs. Okay, so it's going to give us some more information. So to find where those points are, what values of x or whereabouts we're going to put them on the graph, where those additional points are, we need to solve this. So we're solving this equation to equal 0. We're going to find the relevant x values. So let's just write that down how we do that. We say, not that. We say that 6x plus 12, which is the second derivative, which is basically that, equals 0. So we solve for x. This one's linear, so we basically do our algebra, where we first take the 12 over to the other side as a minus 12, and then we get rid of the 6, or we divide it out on both sides to find that x is equal to negative 2. So let's just think about this. We have one solution for an inflection point, and we only have one solution because the derivative equation is linear, so there's only one x value. It doesn't have to be. If you started off with something that was higher than a power 3, than a cubic, you may well be down to a squared equation by this stage here, in which case you'll have a couple of points of inflection. So It's just wherever you're up to with your equation, and how many solutions give you that requirement where the derived equation is set to equal 0. So we found a point of inflection. So there is something going on at x equals -2 in the graph, which we haven't documented already, which is an inflection point that we are now going to investigate using our concavity techniques. So we're going to put those points into a table so that we can do this investigation. The x points of relevance were -3, -2, and -1. We know that at -3 and -1 they're turning points. We're not going to ignore the fact that our first derivative found out that this one here was a maximum and this one here was a minimum. But we're just going to park that information because we're going to use the second derivative now to test those points. So we're going to plug and play second function of -3 into the equation, and we're going to do the same. We're going to plug and play in -2, and we're going to plug and play in -1, the third point of interest. And let's just do that first. So remember that the second derivative equation itself was 6 times whatever x value plus 12. So we're going to try out these x values here. So the first one is 6 times -3 plus 12, which is -18 plus 12, which is a value of -6. The second one is 6 times -2 add 12, which is -12 plus 12, and that gives us a second derivative of 0. Does that one look familiar? So that's how we solved that one previously. That's how we found that point. And the third point of interest, we have 6 times -1 plus 12. And the value for that second derivative is -6 plus 12, which is +6 altogether. What we're also going to do then is do a value that's to the right of -1, and I'm also going to do one to the left of -3. So on the greater side, I'm going to use 0 as the point, only because 0 is easy. So it'll be 6 times 0 plus 12. Which is going to end up at 0 plus 12, which is 12. And to the left side, I'm just going to do it up here. I'm going to do f double dash, so second derivative for -4. So I'm going to plug in 6 times -4 plus 12 there, which is -24 plus 12, which is -12 together. So the values of the second derivative, the values themselves aren't as important as the negativity or positivity of them. So at -4 we had a negative value. So the nature of f dash dash x was negative. Right on -3 we also had a negative value. And at -2 we had 0, which indicates our point of inflection. At -1, we had 6, which is a positive value, so I'm going to put that in there. And beyond -1 at 0, I also had a positive value here. So let's bring back the axes and see what all this looks like. So at -3, we have concave down, and we also have concave down just before it. So let's just sketch what that looks like. Concave down is this, and it could be anywhere along that section. At -2, I have 0, which means that it's turning around or changing, so it's a point of inflection, so something's happening there at -2, which is there, that yellow line. So if I'm concave down, I can see that I've probably got the maximum point here, and I already know that because I did the first derivative cheats test. The graph is flexing or changing here because after that, at -1, we have positive concavity. So at -1, we have, right there, we have basically this shape here. And we also have that beyond there at 0. So we have this same positive concavity here. And there's a turn, there's a change between here and here happening here at -1. So it's a little bit like we're stacking this one and this one next to each other. Oh, I've just figured out how I can do that. So that's happening there, and that in the middle point there is legit a point of inflection. So we can go ahead and trace that in our graph, but before we do that, we've identified everything we need to do. So honestly, it's nearly the end. This is a huge process, but this is Year 12 math methods, and these are the steps you need to do. Before we go ahead and do that, I just want to check the nature of this graph. So that graph was f of x is x cubed plus 6x squared plus 9x, and our mission was to graph it. Now, it's a cubic graph, so we know it'll have two turning points, or it'll be a down, up, down. So, and we also know that it's positive as well. So I've done a previous video where I indicated to you that if the graph itself was an x squared, it would look like that. Minus x squared would be upside down. A positive cubic, like a plus x cubed, is like that. So overall it's going up, and a minus x cubed is coming down like that. And looking at it, because it's a plus x cubed, we can safely go with this shape here, which gives us an indication that what we sketched is actually right. So just by checking that nature, we can go ahead and sketch that graph. Now it inflects here, so we've got that concavity going on, and then it's just sort of flicking around there, so we can note that point of inflection. Then we've got a turn around there, and off it goes into infinity that way, and down it goes into an infinity this way. That's not a very well drawn out graph, so I'm just going to tidy that up a little bit. Okay, that's a little bit smoother. It's still a bit ugly, but it's pretty hard to draw on a whiteboard. So there we go. And I'm just going to carry on with this idea here that'll help you with future graphs before we end it. Now this one here, you can label the graph, and that's part of your steps. We have achieved that using second derivative, which comes from this table here by looking at the nature of turning points, but also at -2 was our point of inflection. I should have put that in there. So that particular type of point of inflection there is a non-stationary. You can kind of think of it as nothing major, no slow turnarounds that gives us a negative gradient in that zone, but rather a very sort of quick flick. So we're heading down and then we're heading back up in concavity. So it's a change of concavity that we've noticed. We went from negative to positive on either side of that point. Okay, so there's our negative concavity, and then up the hill we're going to positive at that point there. So that's a little flick around there, which is called a non-stationary point of inflection. Let me finish what I said I was going to do and look at the x to the 4 graph. If you get an x to the 4, that is basically like a W, and so we have 1, 2, 3 turning points. We had 2 in the cubed, you'll notice here, and we had 1 turning point in the squared here. Let me highlight that. So we had 2, a minimum and a maximum, so it turns around twice, and in a plane x squared it turns around once. We have 1 turning point, a squared. In a cube we have 2, so we sort of have 3 sections, up, down, up, okay, or up, down, or down, up, down. But at x to the 4 we have flicking around again, flicking around again. If we have a minus x to the 4, in case you ever have to plot that, what you're going to be looking for. Now this one here carries on up, so it's kind of got a positive overall nature. Minus x to the 4 will be doing this, so it'll be coming, I've got to think this out now, so it'll end up backwards. So it'll be sort of going down in that direction, okay? So if you see anything like that, you'll be sketching something like that. That's probably the most complex that you'll need to worry about right at the moment. So there we go. Enjoy. Probably the